Okay, so hi everyone. I'm Rohit Kumar Singh, the TA for this course, Nuclear and Particle Physics. This is the fifth live session, which we conduct every Saturday, 4 to 6 p.m. And this course is being taught by Dr. Paulos from IIT Guwahati at NPTEL. So please follow the lectures there before we discuss. Uh, I mean, whatever we discuss here. So it follows from the lectures on the NPTEL because I'll just recap the concepts and show some examples based on those concepts. So for this week, we have mainly scattering concepts of scattering, nuclear scattering, like Rutherford scattering, and then some idea about accelerators. Uh, so like DC accelerators and AC accelerators like cyclotron and synchrotron, stuff like that. So it's good that you have. It will be better if you have gone through the lectures, but I'll try to recap some of the things and refresh some concepts for you. So let's start with that. So uh, so we have the simple formula for scattering. So this is for the classical scattering of suppose there is a hard sphere and there is a projectile, or there are bunch of band of particles going. So for this kind of a scattering, we have the formula. This is called differential cross section. So this is differential cross section, and R is the rate of detected particles. So after these particles hit here, they go into our detectors, right? And so R is the rate of detected particles at around a point theta and phi. So basically you have to imagine a point here having angle theta and phi. So this will be the rate of detected particle at that point. Okay, and F is the flux of incident particles. So number of particles incident per unit area per unit time, and N is the number density of uh, target. So here we don't have, I mean, suppose this sphere is made up of many particles, then we will have some number density, right? And then we are projecting some particles on this sphere of particles which are fixed in space, then this number density will come into picture. Otherwise it would be 1 for a solid sphere. Okay, so yeah, this is for the simple classical scattering. Yeah, do you have any question?
So for the flux F, sir, it's the number of particles per unit volume for the beam, right? Not for
No, no,
the
no, no,
projectile.
no, no. It's a number of incident particles per unit cross section area. So per unit area per unit time. Okay.
Got so that's for the beam that is approaching
Yeah.
the.
So this beam is approaching. You can consider it as a so like a cylinder of beam, and So it has some cross section area, right? This cylinder, the area of the circle. So that is your cross sectional area. So this flux is number of incident particles per unit, that cross sectional area per unit time. And then you have concepts of impact parameter, which is the distance of incident, you know. So B is the distance from the center of this sphere to the colliding particle, I mean the position where the particle collides. So this distance will be your impact parameter. So but the impact parameter doesn't come into the picture here for the differential cross section. Okay, and so in when we go to quantum realm, so there this differential cross section, so you can integrate it over total area, total solid angle, and this cross section is just the probability of scattering. It's interpreted as probability of scattering. Okay, so that's the interpretation. Or in general sense, you can say that probability of something, so suppose in Rutherford scattering, what you do is you bombard a nuclei, I mean you bombard a gold foil with beam of alpha particles. So in that case, the total cross section will be the probability of interaction of alpha particle, or probability of scattering of alpha particle from the gold nuclei. So that's how we interpret this. And so you have the formula for differential cross section for Rutherford, given by this big formula. So this has been discussed in the lecture, so I'm not going in detail, but just to notice one thing, it has a dependence on sine to the power 4 theta by 2. Okay, and this can be checked experimentally, and it has been confirmed. So this is the main feature of this differential cross section. Okay, so do you want to ask anything here?
No, sir.
Okay, everyone left. Okay, no problem. Then let's discuss briefly the one of the accelerator, which is Cockcroft-Walton. Okay, so so how does Cockcroft-Walton accelerator achieve high voltage? This is done through a series of diode capacitor circuits, and so you have a input source like this, and then you have combination of diode and capacitors like this. If you understand these things, I can skip over it, or should I go through it? What do you say? I'll just briefly explain.
Yeah, sure, sure, sir. I saw the lecture in that professor had explained the traveling of the alternating currents and how it sort of multiplies on each junction.
Okay, so I mean, how does it happen? Can you like briefly tell me?
So, sir, the for it starts at the source, and
Hmm.
from the source it goes to C1, and then it goes to that junction over there.
Okay, like here A.
Yeah,
Suppose
at
this
A.
is A, this is B. Yeah.
So it goes at A, and on the next frequency cycle, it goes through the diode and basically multiplies at A. So A receives from the
Wait,
C1
wait,
also.
wait, 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 wait. But you're talking about the positive part of the signal. I mean, when the signal is in the, uh, I mean, when it rises, like positive cycle, right?
Yes, sir. Both cycles contribute
But
to the
in the
multiplication.
positive cycle, the current will not flow through here, right? So
Yes.
yeah, I mean, it depends. It depends on how you start. Oh, sorry. Okay, okay. Let me just go through it. So maybe. Uh, so instead of starting from the positive side, because I have drawn the circuit such a way that, yeah, I mean, we should start from the negative cycle. Okay, so suppose our so for the negative cycle, I mean, so this goes on. Okay, this combination goes on until we achieve whatever we want to achieve. But let's discuss this part. So suppose our input voltage is in the negative cycle. So in this case, this will be the polarity, right? And current will go through this diode, and it will charge the capacitor C1, right? Now, then and it will charge it to peak voltage V naught, right? And then so and then the polarity changes, so it becomes positive, and this one becomes negative, right? And then the current will flow through here. Okay, so basically before the positive cycle, this junction A has voltage V naught, because the capacitor is charged to V naught, so that will be the same voltage of this junction. Now when current will flow through this, flow through this circuit, it will not come here, it will go through here, right? For the positive cycle, because here the diode is uh, you know negative biased, and here this is forward bias, so it will go through here. And so this capacitor will discharge, and no, this capacitor will get charged to V naught C2, right? And so what will happen is, this junction will effectively get a voltage of 2 V naught, because this diode is forward bias, so the voltage V naught here will be the same as B junction. I mean, it will just, because it's become short circuit, this circuit, and so B will get 2 V naught, because it is charging the capacitor. So one V naught will come from here, and this V naught will be the same as the B. And then this cycle repeats, and this voltage keep accumulating until, after n stages you will get 2 NB. So this is how it happens. Do you understand?
Yes, sir. Yes, sir.
Yeah, I mean, I thought that in the lectures it was not covered properly, so I thought I would. Okay, so yeah, and then once you get your desired voltage, you can just transfer it to the beam or the ion that you want to accelerate. So and then there are other accelerators like Van de Graaff and tandem accelerators. I think that those are covered properly in the lecture. So I mean, those are simple ones. Then you understood the cyclotron, the concept of cyclotron, right?
Yes, sir. Cyclotron. Yes, sir.
Yeah.
We use electromagnetic field for accelerating the particle.
Yeah, that is simple. Just yeah, cyclotron is simple. So I'll skip that. Now, then there was a discussion on fixed target collider and colliding and the colliding beam experiment. So there you have seen this derivation that for the fixed target, uh, if you have like so suppose there are two protons, one is projectile and one is fixed, then you get something out of it, and the relation, the mass energy relation comes like this, right?
Yes, sir.
So yeah,
I mean,
this will be used in one of the problems, so I'm just writing it out. And for colliding beams, this is what we get. So p plus p going to x. Okay. So
sir, in the derivation, it is assumed that we are taking the mass of the mass energy of the proton as 1 GeV.
yeah. If you like, no, that is
Uh,
for quantifying. So if you take the mass of proton to be 1 GeV, uh, we will need to accelerate the proton to 50 GeV to get mx of 10 GeV or something like that, right?
so in the while we are doing questions, we don't have to assume that, or will it be explicitly stated that the mass
It
energy of the proton can be?
I mean, in the problem, it should be explicitly stated. Otherwise, mass of proton 1 GeV is a nice approximation. It's 938.27, right? So 1 GeV should be fine. But it should be, I mean, in the problem, it will be given, I guess. Anyway. So yeah, this is fine, but then I wanted to briefly discuss a very important concept, because in the collider experiment, uh, what we use is center of mass energy. Do you know about it? It's denoted by S. So, for example, in LHC, uh, we have center of mass energy of proton as 14 TeV something. Okay. So I wanted to discuss something about this, because there are many problems based on it, if you want to study colliders. So let's first discuss about fixed target. Now, and let's assume that the mass of projectile is equal to the mass of target. So maybe you have, like here you have protons in the beam, and you are bombarding it on a gas of hydrogen hydrogen atom. Uh, so you have many hydrogen atoms, So then the mass of projectile and target will be same. Sorry, mass of hydrogen ions. I mean, you have to ionize uh, the hydrogen gas to get protons, right? Okay. Now, so this is what you are doing. Now, in lab frame, what will be the total energy? So suppose, yeah, I mean basically what will be the total energy? So one proton is moving, right? Other one is
Station.
stationary. So the total energy will be something like p square. I mean this is what we. I mean I'm writing the relativistic ones. Okay. Because these experiments are at relativistic energies, so let's follow the relativistic nomenclature. And this is for the stationary one. This is just because it is the rest mass energy for the target. Okay, and this is for the projectile. Fine.
Yes, sir.
And in center of mass frame, so what is the center of mass frame? Do you know? How you define the center of mass frame?
So I'm not completely sure about it, sir.
So yeah, so the center of mass frame is defined as the frame in which total momentum, the 3 momentum, is 0. Okay. This is what center of mass frame. I mean, this is how you define the center of mass frame, basically. Right. Now, so we have 2 frames, and so we have to calculate the energy, total center of mass energy, but we know energy in the lab frame only, right? So then how to do it? So even if we have 2 frames, the total mass will be the same in both the frames, right? Like whatever the mass in lab frame, that should be same in center of mass frame. Because as I told you, the total the momentum is 0 in the center of mass frame, so this should hold, right?
Yes, sir.
Right. Now what we can do is you know the energy mass relation, so then this will get converted into this equation. So everything here is the 3 momentum. I'm not writing the arrow on the top of it, but you have to think every p as a 3 momentum. Okay. And here you have center of mass energy minus momentum in the center of mass frame, but this is 0 again, right? So what you get is center of mass is equal to energy in the lab frame squared minus momentum lab frame square minus into c square. Okay, and you know the energy in the lab frame, which is this, right? So let's just put it here. So you can see if you square it, you will get a p square c square time. So this momentum PL is just p, right? It is the momentum of the proton, so just remove it. So this p square c square will cancel this one, right? And what you will get is this. So 2m square c to the power 4 plus p square c square. It's fine, or did I miss anything?
So is it two extra or
Which one? This one?
the first two? Yeah.
Yeah, this one should come from this. One mc square is here, one is here. So you are doing EL square, right? So these two will give you 2m square c to the power 4. P square c square will be cancelled by p square c square here,
Yes, sir, sir.
and then
Got
you
it.
have 2mc square. I mean 2ab will be 2mc square into this. Okay, fine.
Yes, sir. Got it, sir. Got it.
Okay. Now, so this is the expression for the center of mass energy in terms of everything. These things you know in lab frame, right? You know the momentum of the particle, I mean of the projectile, you know the mass. So this is fine, right? So let's keep it here. We will use it soon, or let's modify. I mean let's write it in a more convenient way. Now, in these type of experiments, what happens is we accelerate the projectile to a very high energy, right? To a very high momentum. So that means P is very greater than M. Like, so you can write it to match the dimension MC. Okay. So what will happen is this one will be negligible, right? Because it's squared, m squared. So this we will ignore, and and also this we can ignore, right? So what we are left with is sorry, we can take it out of the root. So we are left with 2mc square PC.
So, but how can we take P as much greater than MC? Because if that's the case, then the velocity we are accelerating the particle to will be greater than speed of light.
No, like so what is the mass of proton? It's 1 GeV, right?
Yes, sir.
Yeah, and we accelerate it to very high energies. Like, so I told you at LHC we accelerate to 7 TeV. Sorry, energy is 7 TeV, but so you can calculate the momentum corresponding to it. It will be very high than what we have in GeV.
So, but
It goes to 99.9% of speed of light. How can it go to 100%? Like relativistically, it's not possible, right? To push the velocity greater than a speed of light.
Yes, sir. So then that P is much greater than M. It should be, right? Not MC.
No. This I wrote to just match the dimension. You understand what I want to say? So, I mean, you can write the full, yeah, you can write the full expression. So like p square c square greater than m square c to the power 4. Now it's fine.
Yes, sir. Okay, okay. Yes, sir, yes.
So this will happen when you will accelerate the projectile to a very high energy, right?
So we are saying that the energy because of the momentum is much greater than the energy because of the mass.
No, the momentum is greater. Momentum is greater than the rest mass of the particle when you accelerate it.
So then we can neglect the rest mass ka energy.
Yeah, that's what we are doing. So in this case, energy is just Pc, right? I mean,
Yes.
almost, because the rest mass will not contribute much because the energy. I mean, whatever the energy is coming, it's coming from the momentum. Do you understand?
Yes, sir. Yes, sir.
Yeah. So this is what we get. So center of mass energy will be this. This is the incident energy, or so. Okay, this is for the fixed target experiments. Center of mass energy. Okay. Here only assumption is this, and mass of the target and the beam is, I mean, they are both the same species, so that also helped us to simplify this expression.
So, but we have another term of 2m square c power 4, which will contribute a lot to the expressions, to the
Here,
final
this
answer,
one,
right? Yes, sir, that one.
yeah, this one we also are neglecting, right?
But so the value will be very great, right? Because we are squaring it.
No, I mean, it's 1 GB, 1 GB, 1 square GB doesn't matter.
Okay, sir. Okay, sir.
So, I mean, if you are, so if you are talking on a GB scale, so it's less than 1 GB, so it's 0.97 GB, right? And when you square it, it will become, I mean, again, lesser. So, that's why we are ignoring it. Okay, then let's see what happens for the colliding beams. Now here in the lab frame, first we have energy. So here now both side, so suppose we are colliding protons, so both side it's the beam is moving, okay, and yeah, so energy will be so again we are assuming them to be the same, so mass will be same. This is fine, right? And momentum will be P1 plus P2, and if you are taking P1 in the positive direction, like, so P2 will be, if you write it like this, magnitude and direction, it will be negative, in the negative direction, right? Is it fine?
Yes, sir. Yes, sir.
Yeah. So now, in center of mass frame, what will happen? So in center of mass frame again, we have the same expression. So E L square P L square C square equal to E center of mass square, like we had here. Here, yeah, this thing will be here, same. Okay. And then let's put the EL square from here. So you will get P1 square C square plus M square C to the power 4 plus P2 square C square plus M square C to the power 4 plus 2 P1 square C square M square C to the power 4 and okay, minus, so now PL square C square, so PL is
P1 plus P2.
P1 plus P2, so it's P1 square C square minus P2 square C square, and because we are writing the magnitude, so this will change the sign like this, right? And this is the center of mass energy square. Okay, now what will happen, this will cancel this will cancel this, right? So and these two are what? These two are energy of the beams, right? Both beams, these two. So let's in the lab frame, so let's write it. Okay, you can simplify it. So now in most cases we use the same acceleration in the both beams, so both beams they get accelerated to similar momentum. Okay, so that is, P1 equal to P2, the magnitude is same. We use the same ring for the acceleration, same magnetic field, same everything. So then if you combine this, you will get again 2E1 E2. Sorry, the energy will also be the same, so no, not 2E1 E2. Wait, let me write it. Yeah, P1 P2 will be same, so E1 will be E2, because mass is anyway same, right? So you will get basically 4 E square.
So here we are neglecting M square C power 4, and we are that term
No.
P1 P2 C square.
No. We are not neglecting. You can neglect it. Yeah, you can neglect it also, and then
After neglecting, like the third term mein P1 P2 C square is there, so we
Yeah.
give one C to P1 and one C to P2.
Yeah.
So that's it for energy, and then
yeah,
4 E.
yeah. Okay, so this is now you see the difference. For the colliding beam, it is just 2 times the energy of each beam, but here you have a under root dependence on the incident incident beam energy. So, so this is very interesting, right? So that's why colliding beams are preferred. So, for example, if you will increase this energy of the one beam by 2 times, the center of mass energy will increase 4 times. Sorry, it will also increase 2 times. It will become 4e. But if you increase this incident energy by 2 times, the center of mass energy will increase only by root 2 factor. So that's why it's hard to attain very high energy in fixed target experiments. While for colliding beams, it's straightforward. So this is what I wanted to explain little bit, because these derivation are very hard to find in any books, and I have not seen anyone doing it, but I tried to do it myself, and I worked out. So yeah, this is correct. So this is what I mean. You can Google it. This is what you will get for the center of mass energy for fixed target and colliding beam. So I believe our derivation is correct. Okay, so then let's do some problems.
Center of mass energy is required for what reason? I mean, we have the energy that.
Yeah. So it's the center of mass energy which gets which is available in your experiment for the when we collide two protons in LHC, it is the center of mass energy which will get deposited in the center, and then the new particles will get created. So that we have an estimate of initial energy available in the system. So this is basically the initial energy available in the system, because after the collision these particles they have no identity. Like protons, they are no longer there, right? What is there is the energy that they have deposited, and this is the amount of energy that they deposit, not the energy which we calculate at the lab frame.
Because some of it might be lost in some other ways, which.
Yeah, and so basically one more thing is that experimentally you cannot calculate the 3 momentum of the proton which you are accelerating, but you can calculate the energy of the beam. So this is what we have control over, the energy of the beam, not the momentum of the 3 momentum of the beam. So this is controlled by various RF cavities and the the machinery that is there to accelerate the protons. So that has a simple relationship with the beam energy, but not with the total the 3 momentum of the proton. So that's why the center of mass energy is preferred. So yeah, basically this is the energy available in the system for the to create the new particles. That is the bottom line. So if you pick up any paper of LHC experiments, you will only there will be only mention of the center of mass energy. No one ever mention the lab frame energy or any other energy. Okay.
Yes, sir. Got it.
Yeah. So then let's move to the one problem. So this is a problem from last week's. I wanted to discuss it, but I think because of time constant I didn't. So it's a very simple problem. So let's think about it. So the binding energy of a K shell electron in uranium atom will be modified due to screening caused by other electrons, the finite extent of nucleus as follows. So what will happen to the binding energy of an electron in an uranium atom? Okay, so due to these two factors. So first is screening. So yeah, like you can guess
So
the answer.
definitely screening will cause a decrease in the binding energy.
Okay, so this can be true, this can be true. Then what about the finite extent of nucleus? What will this have an effect?
So it's not gonna, like, the nucleus is not going to be changing any shape, right? So there will be no variation in that. So there will be no variation from the binding energy that comes from a fixed nucleus.
Uh, Wait. No, no. The finite extent of the nucleus will have some effect. But if the nucleus would have been a point, I mean, suppose this is the K shell electron, and if the nucleus, oh, sorry, if the nucleus would have been just a point like thing, and if the nucleus had some dimension, which one will, I mean, there will be some effects, right?
Yes, so but those effects will not change uh, uh, because the nucleus is going to have a fixed dimension. Only the distance between from between the electron and the nucleus might cause any change.
Yeah, yeah,
But that is
but
mentioned here.
see, the distance will, no, the distance is not well defined here. If you have a point nucleus, the distance is okay, r is there. Now you have a finite extent, nucleus has some, you know, it's not a point, it's a finitely distributed charged sphere. So then, I mean, so let's make the picture a little bigger. So this is your nucleus, this is your electron moving in the K shell. Now there are protons and neutrons here, right? So the binding comes from the attraction between the, I mean, the Coulomb attraction between the nucleus and the electrons, right? Now the protons closer to this, closer to the electron will have, you know, high, I mean, will have high electrostatic force than those which are there. If it were a point particle, so that all the charge is situated here, I mean, yeah, then it would have been the constant force. But in this case, situation will change, right?
Yes, sir, but will we for a nucleus we'll assume the distribution of the protons within these energy sphere is equal, like uniform.
Yeah, yeah, it is uniform.
So we can treat the nucleus as a point.
But the distance from the proton to the electrons for each proton will be different now, right?
Yes, sir, but we can just add up the individual effects of each proton onto that single electron,
Yeah, yeah.
and then club them together and just treat it as a point particle.
Yeah, I mean, so that's what we do while calculating the binding energy. But I mean, it's just a speculation. Like, what will happen if you have a fine, like if there is a charged sphere of nucleus rather than a point particle. But there's one more thing is there, because neutrons are there, right?
Also, we can discuss the if we assume, for example, there's an electron. So in each electron is at uniform distance from the nucleus, no matter which nucleus we are talking about.
Yeah.
So a bigger nucleus, a bigger nucleus will have more effect on the same electron in that particular orbit than a smaller nucleus. It will have a stronger effect. So the binding energy must increase with the increase in the
Size.
extent of the nucleus.
Increases the size of the nucleus. That's what you're saying, right?
Yes, yes, sir.
Yeah, yeah, but yeah, that's true. But see, the bigger nucleus will have more number of, so more number of protons. But here we are talking about, same number of protons crunched into a point and then distributed over a sphere. Okay. So then what happened? So so this is a problem of like electrostatic theory. You can calculate uh, what what happens when you have a q distributed over a sphere. What is the force on a point p if you have a charge distributed over a sphere rather than if you have a charge at a point. Okay, so that's the problem is, right? So, like if you go and read any book like Griffiths, you can pick Griffiths. There should be a problem like this, and you'll find that this force will be lower than this. Do you know? So that's why the binding energy will decrease.
Wait, but the force is more, right? So the binding energy should increase, right?
Yeah. No. I'm saying in this case the force is more. So F1, F2, F1 will be greater than F2.
Okay, but
Oh, wait. Yeah. I see. Oh, okay. Yeah. So binding energy more means the electron is bond more tightly, right?
yes, sir. Yes, sir.
And so the force should be more. Yeah. Now, now I understand. So, yeah, it should be. Let me see.
It should just remain unchanged because, like,
No,
if the nucleus.
no. It won't remain. So I think this is what happened. I no, I don't remember exactly, but one of them is greater than the other one. That is true. So that's why maybe it decreases. Okay. It is not equal. F1 equal to not equal to F2. One of them is greater than either. So yeah, maybe because of a charge sphere, you have more, you know.
So this relation can also change, right? F2 greater than F1. So what happens if we keep the sphere dimension as same as constant, but we keep increasing the charge density? So with each charge density, the amount of the electrostatic force that is between the proton and the electron will sort of drop down because the proton that is affecting the electron will be more in a tug with the proton that is inside within the sphere.
Yeah, that is also true.
So maybe after a certain q value, the F1 can become equal to F2, and then F1 becomes greater than F2.
Yeah. That is true. Yeah, if you keep the dimension to be same and then you increase or decrease the density, then yeah, anything can happen in that case.
So there is a chance that F1 can be equal to F2 for varying values of q and the dimensional sphere.
Yeah, it can.
But here we only have the q value. Sort of, not even the q value in this question. We only have the number of protons within the sphere. So we can't like properly conclude if it's going to cause any modification or not, right?
So wait, why not? Because q, like q is the number of, it will be 92 e, right? The
But we
charge.
don't have the dimension constraint, right? Like, okay, 92 protons and how much space?
So space is the so what you are saying? You are saying that if you increase this volume, right, so that the charge density decreases, then there will be a time when the force will be same. That's what you're saying.
If we keep the volume constant, but we keep
Okay.
increasing the Q value,
Q value,
or
but
or
we are asking on we are asking for a fixed nucleus, right?
so what we can do is we keep the Q value constant, but we decrease the volume. So we clump down the protons together as much as possible. That can cause the change in the relation between F1 and F2, right?
It will change, but we are comparing with a point nucleus, okay? So all the protons are crunched into a point, and so whatever if you go towards any direction, like from here you can go only to a finite extent, right?
Yes, sir.
So that will so to become equal, you have to go to a point, and then from the point you have to just you can only get a finite nucleus, and for finite nucleus the force will be different every time.
So, but why are we comparing with point nucleus? Like, there's no mention of the difference between a sphere of a certain charge density and a point consideration of a point nucleus.
No, because so whatever because in the many calculations we assume that the nucleus is a point particle, okay,
No, so
and
for this particular question, they are just saying, will there be modification for the binding energy due to the finite extent of the nucleus?
yeah,
But
so
that doesn't
finite
make sense, right? Because
so fi-
finite extent of the nucleus is constant, so it is staying constant. It won't modify uh, the binding energy for an electron in a fixed shell. That is also mentioned that it's a fixed shell. We are not changing the distance between the nucleus and the electron. So
I don't know. Maybe that would be also true. But what I understood from this problem is that we are comparing from a point nucleus rather. So that's what made sense to me, because we assume every time that the nucleus is a point particle, and then we calculate the force between the nucleus and on the electron, and then if we have a finite extent, like if we have a charged sphere kind of nucleus, then what will happen? So here we see that then the force will be lower, right?
yes, so compared to point particle, it will be lower.
Yeah. So
If you
that's
take the
what I understood.
question, but if you take the question on face value and just
Yeah,
do,
that then what you're saying is true. Yeah, it
then
depends.
the relation between binding energy and a fixed electron for a fixed nucleus just kind
Yeah,
of
then that is not a question, right? That is a
yeah,
fact.
it's there's no proportionality because two
Yeah,
things are constant. We are comparing it to something that is supposed to change,
yeah,
but
yeah.
these two things are constant.
Yeah, maybe, yeah. But yeah, yeah. What you're saying is also true in that case. Okay, then let's move on. Maybe. But what I thought, what the question was saying is this. So yeah, maybe. Okay, let's move on. Let's not give too much time here. Okay, so here we have one problem on the scattering cross section. So this should be based on that formula that we wrote. Okay, so let's read the problem. A scattering experiment is conducted with a beam of flux 10 to the power 6 per meter square per second, and with 10 to the power 3 number of target particles. Okay, a detector of cross section. So cross sectional area of the detector is given, is kept at theta phi, so some angle theta phi, and at a distance of 1 meter from the scattering center. If differential cross section is this, then the number of particles expected to be detected by the detector in 60 minutes is. Okay, so yeah, the problem looks complicated, but let's break it down. So what we have this formula, right?
So here R we have to find basically number of particles to
uh,
be.
yeah, r, not exactly r, so let me, sorry. Yeah, so given is flux, I'm not writing the units, just standard units is there. And then what is given is 10 to the power 3 number of target particles. But in the formula, it's the number density, if I remember, right? Or is it only the number?
So basically number density only.
Yeah,
No, number
yeah.
density, number density.
It's number density. So suppose this is what we have, and n is given, right? So then you can write it like this. So this is for the target, right? So let's say 80. So this is given, right? And then one cross sectional area is for the detector it's given. So detector has a cross sectional area of 2.5 into 10 to the power minus 3 meter square. Okay, this is given. Now should we assume this and this to be same or what? Otherwise we might have problem. But let's see. And what else is there? So the rate is what? Number of particles per unit time per unit.
So for 10 power 3 n, it's written with 10 power 3 number of target particles involved.
Yeah.
So that means these number of particles are involved in the scattering experiment. So we can just take n is equals to 10 power 3.
Sorry, wait. Yeah, these are involved. I mean, these are there, right?
Yes, sir. So we can just take n is equals to 10 power 3.
This one?
Yes, sir. Because it's mentioned separately. Okay? These are the number of particles that are involved in the scattering. Number density is given for the target entire target species.
Yeah.
We do not know how many this thing will partake in the.
No. But I'm saying. So these are the number of target particles involved. Okay. No. But this is number density, right? This is always number of particles that are there in the target divided by the area.
Yes, so that's for finding. So F dot capital N will give us basically the number of target particles that are being involved in that particular flux ka cross section.
F dot N will be number. Yeah, wait. No. F dot N will be so this is number of particles, incident particles. Okay, this is flux is always for the incident particles. Okay, so number of incident particles per unit area per unit second, and you are saying if you multiply it with 10 to the power 6, it gives you 10 to the power 3. What you are saying?
No. So I'm saying that we can just take n value, the F dot n.
I see. Wait. Yeah, see. You are saying this, right?
No, sir.
Yeah, no.
I'm saying n, the capital N is there, right?
Yeah, capital N is there.
So that is the number of. This is what I'm saying. We just take n as 10 power 3. And we know as number density of target particle.
Yeah, this. How will we know the number density of target particles?
So we while setting up in the lab, that will be. It is something that they should give, but here they're given 10 power 3 is the number of target particles involved.
Yeah.
So they are not giving us the total n value. They are giving us only the number of particles that are involved in the scattering.
Yeah,
which will be different from the n value, right? The number density of target particles.
Okay. So you are saying that whatever the flux of incident particles is coming, it's interacting with 10 to the power 3.
Yes, sir.
So you are saying number of incident particles will also be 10 to the power 3. right?
Uh, no, no. I'm saying that these number of particles, 10 power 6 number of particles, are only going and hitting the 10 power 3 target particles.
Okay.
So if we go back to the original equation, which is d sigma by d omega is equals to r by f no, fn,
Mm-hmm.
r is the particles hitting the detector,
Yeah.
and Nietzsche in the denominator is this, it is the number of particles that are basically scattering off the target.
Yeah, yeah, yeah.
So f dot n can be as 10 power 6 into 10 power 3 directly. So here we can just take the f dot n, the n is there, we can just take it directly as 10 power 3. Rather than writing n is equals to n by 80 and then
Mm-hmm.
like finding 80 or assuming AD, the area of the detector is equals to the area of the target. This
Are
thing.
you sure? Have you done this problem? I don't know if
No,
that
no, sir,
can
but
be
like
done.
because that statement is throwing me off. Number of target particles involved.
Yeah, yeah, yeah. I see. Yeah, what you're thinking is right, but I have not thought it like this. So let's see. So then, so we have a flux density, that means 10 to the power 6 particles are coming per unit area per unit time, okay, and they are interacting with, and totally over time they have interacted with 10 to the power 3 number of target particles over all time, right?
Yes, sir.
Yeah. Okay. So so then mm-hmm.
So in mathematical language, that would mean that we just multiply both of them, right?
Yeah, yeah,
To
if
get
you,
the
if you
total.
multiply it, yeah, I understand. Don't know, if you multiply it, this much have gone to the detector to get detected, right?
Yes, these are the number of particles that should be detected
That
by
should be detected per unit area per unit
time.
time.
Yes,
Yeah,
yes, sir. Yes, sir.
yeah, that is true. Okay, forget this formula. Okay, that is true. This number of particle should be detected per unit area per unit time. Then if you multiply it with the cross section area of the detector, which is this number of particle is detected per unit time, right?
Yes, sir. Or we can just
And just multiply it with 60 minutes or 60 into 60, right?
yes,
This
sir.
is the total number of particles in 60 minutes that are detected. So let's calculate this and let's see if we get our answer. So what will it be? Can you just, you can, okay,
Yes, yes, sir.
let me
Just a
do
second.
it.
Sir, or other than that, like, can we also we have d sigma by d omega.
Uh-huh.
We need to find r, so we just send 10 power 6 into 10 power 3 that side.
Yeah,
Um,
yeah, that is also true. No, 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 wait.
10 power 6, 10 power 3 into 2.5 into 10 power minus 3,
Mm-hmm.
because that time, that side where we don't have time unit. Wait, just seconds, I'll just calculate this value.
No, no, let's first let's calculate it. Let's see if we get our answer without the cross section, using the differential cross section. Uh, it is like this. I don't know. So what you are get, yeah, that what you should get is very high number, right? And it
Yes, sir.
should be high number because 10 to the power 6 particles are coming. Mm-hmm.
So what is this? 17.5 goes to 18.
No, no, no. This is the range. What is that is given
Okay,
in the.
okay. Sir, is 17.5 into 10 power something or
No,
just 17.5?
it's just this is given. Maybe something is missing here. I don't know. But okay. No. Okay. What you got?
So I got 9 into 10 power 9, sir. I got a big
Okay,
number.
okay, okay. Now, yeah, okay, yeah. If you multiply naively with this number, you get this, which is the answer. Now, what is this?
Oh, yeah. Oh, we forgot. This is the denominator. What the denominator? Then we send it to that side,
Uh-huh.
which is given. We have the value for d sigma
No,
by
no,
d.
no, 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 no. Let's forget the formula. What we are doing is right. Okay. We were just going through logic, right?
Yes, sir.
Now, where will this number come from? Can you tell me? Why we have to multiply this number here? Just by logic. Forget the formula, everything.
Um,
Why you have to do it?
mm,
Because this is the probability of interaction. Not all the particles that are
uh,
hitting the target is interacting, right?
these are the particles that are scattered into the particles that have the probability of being
Yeah, exactly.
detected.
So there's a probability involved and it is very low. You see, it is 10 to the minus 9, the order. So that's why you will have only 18 particles in your detector.
Yes, sir. So answer. No need for formula.
Yeah, I mean, this is nice, yeah. Yeah. But yeah, from the formula you can also do it. It's straightforward.
Yeah. Formula will be.
But I mean, the formula is also derived like this. So what we did is correct. Okay. Yeah, this is very nice. Thank you. So okay, we have another one joining. Adrija, did you understand how we calculated it?
Actually, it was a bit confusing, but then again, like it's my first time learning nuclear physics,
Yeah,
so
yeah, it's okay, it's okay.
eh,
I can go through it again. Yeah, let's for my own understanding also I can go through it. So we have this problem. Okay, I'll I'll erase everything and we will do it again. So yeah, let's do it again. So the problem says that there is a beam of flux density 10 to the power 6 means 10 to the power 6 number of particles are incoming, okay, per unit area per second, okay.
yeah.
And then there are, and these 10 to the power 6 number of particles, they are interacting with 10 to the power 3 number of target particles over all time, okay. So that means these 10 to the power 6 number of particles, so these are like this, and then you have a golden foil or something, there are some particles, so these are coming, hitting, and then going to our detector, okay. So now you have to understand. So 10 to the power 6 into 10 to the power 3 number of particles are detected by the detector oh wait, no, we'll have to multiply the cross section, yeah. No, so what cross section means is it is the probability of interaction. No, 10 to the power 6 particles are coming and hitting the detector, but all of them are not interacting with the target particles, okay. So this much should, so we are multiplying the cross section. So only this much should interact with the target. Okay, this is the probability of interaction, so we are multiplying it. So finally this number is what get detected per unit area per unit time. Okay, so to calculate this number for 60 minutes and for an area of this, we'll have to just multiply them together. Uh, 2.5 and the number will be 18. Is it fine, Adnan?
Yeah, I got it. It got clear.
Adnan, is it fine? I mean, this approach is, I think, more suitable rather than.
Yes, sir, this is more intuitive.
Yeah. So, yeah, this way you can also think about it, and then you have the formula that I wrote: d sigma by d omega r f n. So you can put these numbers here. So this is given. You have to calculate this. Flux is given, and the number density. So the problem is this number. This is number density, but only the number of target particles is given. So what I was thinking is maybe we can write this as n by a, and then there is one a factor coming from here. This should be same, and then they will cancel, and then you will finally you will have everything. So that way you can also like approximately get this value. I mean, you will anyway you will get this value using this formula, but intuitively it is more interesting to solve it like this. Okay, so yeah, let's move on to the next problem. So this is a problem on Rutherford scattering. So these are very simple problems. I'll go quickly through them. So in a Rutherford scattering experiment using alpha particles as projectile and gold foil as a target, a detector recorded n number of events in 1 hour. Now how many events would be recorded in 2 hours in the same experiment? So anyone, any guesses? So n events in 1 hour. So what about 2 hours? You will get 4n, you will get 2n. I mean, n is always wrong. You will get something, right, in the next hour, or you will get n square. What do you think? Any guesses?
So here can we use that the Rutherford scattering equation, right? I think you had given us.
Yeah, I think I have wrote it somewhere. Yeah, this. Does it help here? I mean, I mean, there's nothing like. It's simply 2n, right? So if you would have something, t like time dependent in that equation, or like any scattering, it doesn't depend on time, right? Like with time it doesn't changes, nothing changes. Whatever statistically it should be independent, like first hour and the second hour. If you are taking a long enough period of time, you should get same number of events. If if your flux is constant, whatever you are projecting, if it's constant, then you will get same events at the end. And also your target should not deplete much, right? So this is the basically, I mean, simple experimental observation. Yeah, is it fine? Do you have any doubt?
Yes, that makes sense.
Okay, yeah.
Yes,
So
no doubt.
Yeah.
For
Adrian?
scattering, if is it possible for us to assume the particle that has been scattered from the from a target particle
Mm-hmm.
is a particle coming from the target particle, so we can treat it as like a decay?
No, scattering is not like a decay, right?
No, that the original formula for the parent formula for decay was n is equals to forgot.
No, no, no. So decay is a different thing. Like decay happens when you have something which. So suppose this is a projectile bombarded on a target, and you get something which is not stable, and then this decay into something. Okay, but what happens in scattering is projectile gets deflected. I mean, it changes the nucleus in some way, but the same thing comes out. Whatever goes in, it comes out, just at a different angle. I mean, this can also change.
So like
In so
yeah,
this
if
is
we
what we
assume
call
the second,
inelastic scattering or something.
so if we assume the second example, then that the original formula n is equals to n naught e power minus gamma t.
Yeah.
Over there, we can
No,
consider.
no. That is that is a radioactive decay formula. You can how can you apply it here?
No, that's what. So over the, if for scattering we assume gamma is a probability for the nucleon to decay. So here we assume gamma as the probability of the particle hitting the target particle, and n naught is the density of target particle, and time is the time for for observation of the particle.
No. The radioactive decay is very different thing that you have here. See, the in radioactive decay, you have some nucleus sitting somewhere, okay, and because it's unstable, it keeps emitting particles. I mean,
Yes, yes.
set of some bunch of nucleus sitting somewhere, and it is emitting particles. But here you have a, I mean, so like gold, first of all, gold nucleus is stable, so it won't decay, right? What
Yes, sir.
maximum what can happen is I mean, one or two protons maybe get. I mean that will also not happen. Maybe just momentum might change. Some amount of energy transfer can happen, but I mean this formula is cannot be applied here in any case. So, and we are taking, so we are not talking about very short amount of time. We are talking about 1 hour. So on average the number of events should be same, both time scale. Yeah, maybe in 1 second you might get some different number of events, but over a large time range the average events should be same. I mean that's what happens in any experiment, unless your like I said, unless your flux is changing or luminosity is changing. But yeah, let's not go into that. Should I move on? Yeah, you can
Yes.
think about it more if you want. Okay. So yeah, this I think we already discussed this one, right? So in a fixed target collider scattering experiment with a proton beam of energy 97 GeV, so we have a proton beam of 97 GeV, and it is sent to a collection of protons, hydrogen ions, which is at rest. So if it's a fixed target experiment, and the mass of the heaviest particle that can be produced in such a collision is mx. So basically p plus p going to x. Okay, so this proton will hit this hydrogen ions, and it might produce a particle x with mass mx. Now if you change the setup so that instead of a fixed target, you have two proton beams of equal energy colliding, bumping into each other, and creating the same mass mx. So again you have this thing, but now both are moving. Okay, here this one was moving, this one was stationary. Here both are moving and colliding. So the minimum energy required is what? So here you required 97 GeV in one proton beam to create this particle of mass mx, and we can consider the proton to be of 1 GeV mass. So we have the formula, right? We have this formula for fixed target. We have this one, right? So what is given? So mx is same mass of proton we have to take. So I'm not writing GeV, everything is in GeV, so let's skip that. So 2 into 1 plus, so energy of the proton beam is 97. So mx square is what? 98 into 2, which is 196. Okay, and then for the colliding beams, so this is for fixed target. For colliding beams, we have mx is equal to E1 plus E2, and it is given there both the beams are of equal energy, so it's 2E. Sorry, why I am writing E2. Okay, so you can calculate E mx by 2. Wait. Oh, this is 196, so mx will be what? 14, right? 14 square is 196, or?
Yes, of course.
Yeah. So then this will be 7 GeV. So now you see the difference. You needed 97 GeV to produce 14 GeV particle, but you need only 7 GeV proton in a colliding beam to produce this 14 GeV particle. So yeah, this is a simple problem. So for those who don't know these formulas, you should go and check the lectures. These are simple expressions that are derived for fixed target experiments and colliding beam experiment. Okay, any question here? I guess not. Okay, this is a question again on collision. So yeah, it's a simple one. So you all know about Higgs boson, maybe you have heard about it. It's called God particle, I don't know why. So it has a mass of 125 GeV, and it's produced at LHC in the collision of two high energy protons. So protons collide and they produce this Higgs. Okay, so we know that the proton has 931 MeV rest mass energy. So how does two protons of 91 MeV gives us a Higgs boson of 125 GeV? That is the question. It's a simple question, right?
For all first three options seem right, no?
All
First,
first three options.
first two options like
Yeah,
these.
yeah, these are facts. I mean B, C, and D. They are facts. So all should be
Uh,
true, but the main reason is this one.
A1.
Yeah, yeah, yeah. So the protons are accelerated to TeV energy. So like I was mentioning sometime before. So right now protons can be accelerated at LHC at 7 TeV energy. So we observe a center of mass energy of 14 TeV for the proton-proton bunches. This is
This answer should basically be LHC uses high magnetic field in a circular
yeah,
accelerator to
yeah,
accelerate
yeah.
proton to
Yeah,
EV
right.
energies. That's what makes sense here.
Yeah, yeah, that makes sense.
Basically, we need to form a very big answer using all the options.
Yeah, I mean in this case, like, but see, it's not that only circular accelerator will give you such high energy or high magnetic field. So high magnetic field will basically bend the uh, particles. It will not accelerate, right? Magnetic field is used only for bending the beams in the LHC, and luminosity is just more number of events, more number of particles per bunches. So that is also not the only thing that you need. So this is the most important thing. Like you have to have accelerations up to TeV energies. So I think that's why only A option should be correct. These are facts. Obviously, these are facts, but these are not the reason that gives you this energy.
So also beam luminosity option,
No.
we don't need to consider because it's clearly mentioned only two high energy protons. So there is no
Yeah, yeah,
luminosity
yeah. The
changes.
collision. Yeah, yeah. This option is anyway doesn't make sense. Okay. So yeah, let's move on. Uh, this is a boring problem, but we can do it. So a proton is moving with a relativistic factor of 0.948. What will be its kinetic energy? So should I do it? I mean, can you guess which option should be correct? So relativistic factor of 0.948 means
Gamma, right, sir? Gamma is
no,
equal
no,
to
it's
V by.
beta. It's beta, which is V by C. So so this is what tells you that how much velocity the particle has and the proton has. It's 94% of 94.8% of speed of light. Speed
So
of
what is gamma then, sir? That 1 by 1 minus V square by C square, root of 1 minus.
Yeah, gamma is so gamma is sorry, gamma is this thing, right?
So what is this thing called?
This thing is called this thing. Yeah, it has it has a name that I have also forgot, but it should be. I mean, it's also less than one. It should be also less than one, but it's the relativistic factor is this that I know. Okay. So then, yeah, can you make a guess? What should be the answer? At 94% of speed of light. So 943 MeV is very close to the rest mass energy of proton, right?
Yes, sir.
Yeah. So it should be more than this. So I will guess this option is correct. So you can try to calculate it. You know that kinetic energy is what? total energy minus the rest mass energy for the relativistic case. Total energy is gamma m naught c square. So m naught c square is the rest mass energy, gamma minus 1. So you can calculate it, right? So 938.27, whatever you get the gamma to be, so yeah, it will come around this. Okay. This one is trivial. So if there are n stages in Cockcroft-Walton oscillator, the maximum voltage achieved is 2 nV. We know that. So I discussed this in the beginning. Drija, you were not there, but if you go through the lectures, this is also discussed there.
Yeah, it was there.
Yeah, okay, thanks. Then we come to a problem which I wrote myself just to get a feeling of what I derived earlier. So the problem says find the ratio of factors by which center of mass energy increases as we double the beam energy in fixed target versus colliding beam experiments. So I derived these formulas. You can check if you have not. If you are not there, you can maybe check later the recordings of this lecture. So for fixed target, the center of mass energy is given by, so it is not the exact, it's approximation, but for high energy experiments this approximation works fine. So this was 2 mc square energy of the incident beam, and for colliding beams the center of mass energy is simply 2e. So if we double it, the ratio will be simply, so if you double this, it will have root 2 factor. If you double it, it will have 2. So this is the ratio. So 1 over is 2. So this just simply says that achieving a higher energy in fixed target experiment is hard than if you have a colliding beam. So you can increase the beam energy and it will just reflect by the same factor in the center of mass energy in the case of colliding beams, but that doesn't happen in the fixed target experiment. So nowadays everywhere we have colliding beams. Everywhere high energy experiments we use colliding beams. Okay, so yeah, this was the last problem. Do you have anything to ask here? If not, yeah, this was the last one. So thank you all for joining and interacting. Yeah, so we'll meet again next Saturday. Bye bye.
Thank you, sir. Bye, sir.
Bye.
Thank you, sir. Bye, sir.
Bye.